Welcome to our talk about learning generic local shape properties for adaptive supersampling. In voxel-based geometry rendering, sparse voxel trees, short SVO, are commonly used as acceleration structures to identify voxel ray intersections at interactive speed. When shading a pixel, its corresponding view ray is intersected with the SVO to retrieve the shading information stored at the intersected voxel. Further, SVOs can be equipped with a level of detail structure by storing average shading information such as luminance and surface normal at intermediate nodes. By intersecting with intermediate voxel nodes that project to the full size of the shaded pixel, anti-aliasing and reduction of temporal noise during camera movement can be achieved in a similar fashion as bitmaps in textured surface rendering. However, this approach assumes that all shading information that is averaged over contribute equally to the shaded pixel. This is not true if the local geometry is represented by the intersected intermediate node shows self-occlusions for the current view direction. For instance, consider a mountain peak lit by the sun, with luminance 1 on the lit side and luminance 0 on the shadow side. An intermediate voxel covering the peak will have an average luminance of value 0.5, which is correct when viewing the peak from the top. But when viewing it from a flat angle, one side of the mountain is occluded and the estimated luminance of 0.5 becomes in fact bad approximation. Even worse, part of the shaded pixel may not even be covered by the mountain, so that it is required to blend in some sky color as well. This information is completely lost on a pixel scale level of detail. Supersampling patterns attempt to identify those cases and compute improved estimates by tracing and blending multiple rays for critical pixels. Commonly, supersampling patterns were derived by utilizing screenspace information such as pixel color or G-buffers from a one sample per pixel rendering. If variations in appearance between a pixel and its neighbors become significant, a higher sampling count is issued for this pixel. In general, adaptive sampling techniques for Monte Carlo rendering can be applied to one sample per pixel renderings as well, by artificially increasing the sample count with the neighboring pixel samples. Hence, works of Lee et al., Mitchell, and Rüdiger et al., just to mention a few, can be applied. On the deep learning side, Screenspace importance masks were successfully trained to solve supersampling and denoising tasks. These masks can also be utilized to derive supersampling patterns in level of detail applications. Here we refer to works of Kuznetsov et al. And Weiss et al. Unfortunately, Screenspace approaches that basically supersample edges cannot detect settings in which neighboring pixels are assigned similar but consistently wrong appearance. This commonly occurs for regular fence-like structures where gaps between layers are not preserved at coarser scales, as well as stacks of close-by thin geometry sheets that are merged at low level of detail. We argue that Screenspace approaches do not attack the issue with level of detail rendering at its core, namely occluding geometry. Instead, we propose a Worldspace approach that considers local geometry at ray voxel intersections when reasoning about supersampling. It builds upon an oracle function f that takes a ray voxel intersection point p, as well as additional rendering parameters theta that describe the projection to the shaded pixel. The oracle returns an occupancy value sigma that describes the fraction of the pixel covered by local geometry around p, and it also returns the average luminance L projected into this fraction. Now for each ray intersecting with the sparse voxel tree, we evaluate the oracle function and check if the returned occupancy value is close to 1 and if the returned luminance is close to the luminance stored in the intersected voxel. If either condition is not satisfied, supersampling is issued. An example supersampling pattern here, derived with our approach, can be seen on the right. Here, red shades in the image hint at higher supersampling rates. One can implement the perfect oracle function by rendering the local geometry around the intersection point P into a high-resolution viewport representing the current pixel, and then deriving occupancy and luminance from there. Clearly, this would violate any real-time constraint. Instead, we realize the oracle function by training an encoder-decoder network architecture that we call Patchnet. The encoder takes in local geometry patches from the current scene and transforms them into latent feature vectors, so-called patch codes. Together with the view-dependent rendering parameters, the subsequent decoder is able to interpret the patch codes and derive occupancy and luminance. Our design comes with several advantages. First, Patchnet does not depend on a specific scene, a dependency which otherwise is common for geometry encoding networks such as scene representation networks. By depending on local geometry information only, Patchnet immediately generalizes to arbitrary scenes that are composed by similar geometry patches seen in training. As observed in our work and other works by Yang et al. And Liu et al., the space of plausible local geometry shapes is rather limited. It can be encoded in a low-dimensional feature vector. In our experiments, it suffices to train a 10-dimensional patch code to solve this supersampling task and generalize to other datasets. As a second advantage, the encoder-decoder structure of Patchnet allows to compute all scene-specific patch codes by executing the encoder of the network in a pre-process. During real-time rendering, only the lightweight decoder has to be evaluated per pixel, thus relieving a large chunk of computational burden introduced by the overall architecture. The pre-computed patch codes are organized in the same sparse voxel log tree that represents the geometric model. Specifically, we store a patch code for each voxel corner arising in the SVO. Consider the following 2D scenario, showing a 2D voxel at level L with its 4 corners. For each corner, the corresponding geometry data is extracted by sampling a centered block of r to the power of 3 fine voxels at level L plus delta, where r equals to 2 to the power of delta plus 1. The parameter delta defines how many levels of detail Patchnet can look ahead when reasoning about supersampling. The average shading information stored at the fine voxels is written into a dense grid, which then is passed to the encoder to derive at the patch code of the voxel corner. We found that the encoder can be efficiently realized by flattening the grid and processing it in a multilayer perceptron with 3 hidden layers of 256 channels each. For each ray voxel intersection during rendering, the patch code at the intersection point P, here visualized with a red cross, is obtained by reading off the patch codes from the intersected voxels corners and trilinearly interpolating them according to the location of P. The resulting feature vector acts as a neural representation of the local geometry. It is concatenated to the rendering parameters theta for the current pixel, and then processed by a small-scale multilayer perceptron with 3 layers of 48 channels each. We train Patchnet end-to-end on geometry patches taken from a sparse voxel tree representing a sufficiently complex scene. Each training sample is generated by drawing a random voxel at level L and extracting its geometry patch at level L plus delta with resolution r equals to 3 times 2 to the power of delta. The ground truth is obtained by rendering the geometry patch into a viewport with randomly sampled rendering parameters. The patch code input of the decoder is computed on the fly by invoking the encoder on the 8 subpatches of G belonging to the 8 voxel corners. The decoder then outputs occupancy and luminance predictions, which are compared against the ground truth via an L1 loss function. Finally, the gradient of the comparing loss function is backpropagated through the single decoder and 8 encoder invocations to update the network's weights. To evaluate Patchnet, we have voxelized 4 different scenes: the San Miguel inner courtyard scene, a bisected sponsor scene, and detailed CAD models of an airplane and power plant respectively. For San Miguel, we removed most plants and baked global illumination effects with the cycles renderer of Blender. All other scenes were diffusely lit from 2 antipodal directional light sources. For all datasets, we compose camera tracks of 2000 frames that start far away, then close in over 1000 frames and finally explore the scene's detailed geometry in another 1000 frames. The resolution of each frame was chosen as 130 × 130 pixels, so that level of detail effects are noticeable in most frames. Depending on camera location, the scene may not cover the whole viewport, especially in long-distance shots. Each pixel for which at least one geometry intersection is registered in its surrounding 3×3 neighborhood is called an active pixel. The remaining inactive pixels showing background are considered to be outside of the scene and never will be supersampled. We evaluate supersampling approaches that all rank active pixels according to a specific score, and then mark the top X% scoring pixels per frame for supersampling. The quality of a supersampling approach is measured by computing the mean squared error over all active pixels in a camera track, where supersampled pixels have an error of 0 and one-sampled pixels have an error corresponding to the difference between a 1 sample per pixel and 32 × 32 samples per pixel rendering. Specifically, we consider 6 scoring functions. The first 4 are fueled by Patchnet after training it on one of the 4 datasets respectively. The scoring is given by the deviation of predicted occupancy from 1 + 5 times the deviation of predicted luminance from the intersected voxel luminance. The fifth one is given by measuring variance in luminance over the 3×3 neighborhood of each pixel in the 1 sample per pixel rendering. The last scoring function is obtained by passing the 1 sample per pixel rendering to the network of Kuznetsov et al. And extracting its importance mask. Here we can see for each camera track how the mean squared error changes when varying the budget X of active pixels that may be supersampled. The X-axis denotes the available budget, whereas the Y-axis denotes mean squared error. Note that for all scenes, Patchnet fuel scoring functions depicted by dashed lines consistently outperform reference methods over broad ranges of X, independently of the dataset Patchnet was trained on. That is, Patchnet generalizes to new scenes. For instance, when supersampling 30% of active pixels in the airplane scene, all Patchnet scoring functions achieve half the mean squared error compared to reference. On the downside, Patchnet comes with a significant memory overhead in the pre-computation stage, since the patch codes have to be stored in the SVO. In future work, we plan to reduce the overhead by means of float quantization, varying the patch code dimension and eliminating redundant patch codes at the deepest delta levels of the SVO. Further, we plan to speed up inference timings of the decoder significantly by applying recent work of Müller et al. And Weiss et al. That utilize tensor cores to run small-scale MLPs directly in shared GPU memory. In spite of such improvements, we believe that Patchnet will be inferior to brute force 4x supersampling, since casting primary rays in our application is very cheap. We consider our work as an intermediate step for deploying Patchnet in recursive ray tracing applications where high sampling costs justify high-quality supersampling approaches to discard dispensable samples. With that being said, I want to conclude the talk. For further results and discussions, please refer to our paper. There, we shed light on the effects of the look-ahead parameter delta, and we also highlight some specific frames with geometric structure that cannot be resolved by any screen space-based supersampling approach. Thank you for listening.